Hello everybody, so welcome to the afternoon session. I have broken some sprinting records on my way here, so I would like to welcome you again on behalf of the Department of Athletics at ICTS Pune, and I'm happy to introduce the first speaker for this session, Dr. Riddhipratim Basu from ICTS TIFR at Bengaluru. His title is First Passage Percolation, Questions, Conjectures, and Results.
Hello, everyone. First I would like to thank. Yes. Am I audible now? Okay. Yeah. So first, I would like to thank the organizers for inviting me, and I'm very glad to have the opportunity to come back to ICTS Pune after quite a while. So given that the audience is quite broad, what I will try to do for this talk is that I'll introduce to you a very interesting, at least I and many others find it a very interesting model in spatial probability, and I'll tell you mostly about very interesting questions, open questions and conjectures that are there in this model of first passage percolation. There will be some results also, but as you will see, the results are so far, although this model is being studied for more than 50 years, the results are quite unsatisfactory, as you will see. So there are many interesting open questions and very interesting conjectures in this model, which we don't know how to solve at all. Okay, so let me start with defining the model. So as you can see here, I have drawn a piece of the nearest neighbor lattice of Z2. So in general, we'll work with ZD. So we'll work with the nearest neighbor. And I'll denote by E of ZD the set of all edges in the lattice. And the model, the randomness in the model will come from a set of independent and identically distributed random variables. So they will be positive. You can take them non-negative with certain assumptions, but we will just consider them positive. So what we will do is that we will assign a random positive weight to each of the edges in the lattice. Okay, so as you can see here, I have marked. So this edge has weight 3, this edge has weight 1, this edge has weight 6, and so on. And then what we will do, we will consider paths in the lattice. So let's say this point is the U and this point is V. And I consider this path that joins U to V. Let's call this path gamma. And then I define the weight or the passage time or the length, depending on your perspective of the path, to be simply the sum of the weights on the path. Okay, so in this case, it is 1 plus 6 plus 1 plus 1 plus 2 plus 2 plus 3. That is 8, 9, 13, 16, if I'm doing it correctly. And I define this weight for every path connecting U and V. And the observable of interest is the following. So I look at all paths connecting U to V, look at their weights, and then take the infimum over all the weights. So since I'm not putting any restriction on the path, there are infinitely many paths that join U and V. So it's an infimum, but one can show under certain natural assumptions that this infimum is actually attained. It's actually minimum. So as you can see, this what I'm doing. So if the weight of every edge was 1, then this TUV would simply be the graph distance between U and V in the underlying graph. So what we were doing, basically you can think of if you are coming from more of a geometric point of view, it's a random distortion of the graph distance metric. So I had this underlying graph distance on ZD, and then I have randomly distorted the metric by introducing these random weights or random lengths on the edges. But this is not how the model was originally introduced. The original motivation came from statistical physics consideration. You can also interpret the model in the following way. So suppose I start with some fluids at the vertex U. And these weights are simply the time it takes for the fluid to flow through that particular edge. So in that case, we can easily check that TUV would be the time it takes for the vertex B to become wet. So that's the statistical physics motivation. So you are trying to understand flow of fluid through inhomogeneous random media. That was the statistical physics motivation for introducing this model. So this was introduced by Hammersley and Welch in 1965. So 58, 59 years ago. Okay. And so what are the kind of questions that we want to understand? What are the basic questions that we want to understand this for this model? We want to understand the large-scale behavior of the metric. So let's say, clearly, since the underlying environment is translation invariant, I can simply take U to be 0. And I can study the large-scale behavior of T0V as norm of V becomes large. That's one question. And a very related question is the behavior of the metric ball. So if you look at BT, which is a set of all the and then I want to understand what happens to B as T becomes large. Okay, so from the point of view of studying a random metric, these are the two most questions. And there is one other question which it turns out has very intimate connections to understanding the first answers of the first two questions. That is the behavior of the geodesics. So behavior optimal paths. Okay, so as I said, under rather minimal assumptions, one can guarantee that there would be a path gamma which will attain the infimum in that definition. And as U and V becomes far and far away, we want to understand how does that optimal path. Well, okay, so under some further assumption, you can also say that the minimizing path is unique, and we want to understand how does that path look like as the distance between the two endpoints becomes. Okay, so these are some of the basic questions. Now, certain results are quite easy to obtain. The first order behavior. So let's just do some basic calculation. So suppose I want to understand this. So I want to understand the metric from the origin to m plus n. I mean, I can go in any direction, but let's just for sake of clarity, let me just go in the first coordinate direction. And let us try to compute this point. I'm starting from 0 and going to m plus n times p1. Now, of course, since I'm looking at the infimum, this is this quantity. So let me first remove the expectation and see very easily. It's a triangle inequality for the metric, right? Okay, so now when I put the metric back in, put the expectation back in, by translation invariance, expectation of this quantity is simply the expectation of the metric between 0 and n times E1. Right, so the underlying field is translation invariant. So going from m times E1 to m plus n times E1 is the same as going from 0 to n times E1. Okay, very easy. So now the analysis 1, what is called Peckett's lemma or something, that will tell you immediately that expected value of T0 and E1 divided by n, convert this to some constant. This is the basic property of severity sequence. Now this mu, of course, depends on the direction E1. It also depends on the distribution F. Okay. And you can also see that there is nothing particularly special about the direction E1. You can have the same result basically along every rational direction. And by some continuity, you can piece these together. Now, these different convergences along different directions, you can piece them together to get what is called the shape theorem. Again, so these results all hold under some basic moment assumptions on F. I'm not going to write down specific assumptions that are needed, but one knows exactly what sort of assumptions are needed. So what is the shape theorem? So recall that definition of Vt. So if you look at Vt, now Vt is a discrete subset of Rd. So we want to actually pattern it so that it will be a proper, I can talk about convergences. So let's just do this. So instead of just looking at the vertices, we're just making it into cells. So we're just looking at a unit cube with center at those vertices. And then essentially by piecing together these results, okay, so I should say one more thing is that there is a version of the Peckett's lemma for subadditive sequences for random variables. This is called the King-Bank subadditive ergodic theorem, which will let you also upgrade this to an almost sure and L1. So this is called King-Bank's subadditive ergodic theorem. It's not, the particular formulation of the theorem is not very important for us, but you should just think of this as a version of a Peckett's lemma for random variables. Okay, so by using this for all directions together and patching things together, one can show that the set of all wet vertices at time t, after I have patterned them, when I scale them by t, it converges to a compact convex set in Rd with non-empty cubes. Okay. So the picture, what it would look like is that. So if I draw the, so this is my set Vt at time t. So as t becomes large, there will be some limit shape that it will converge. Okay. So the next question, a very big question which is wide open, is to understand what is B. What is the limit? So this B is called the limit shape of the model. It depends, of course, on the underlying distribution. Okay, so it's a very big open question in the area to understand what is B. So there are many conjectures about it, and partly from numerical simulations that you can do to see what this shape looks like. So conjecture 1 is that mild conditions now. Okay, so when I say mild condition, it typically means that it has enough moments. And
so this extra term, the Q you added in the limit, it doesn't make any effect, right?
Which
is minus half to the D.
So this is, I'm talking about, so this is the convergence of sets. Right? So I'm talking about convergence in chromoplastic topology, something like that. So if I don't add this is just going to be a subset of ZD. So I cannot talk of convergence of that to a subset, a non-trivial subset of RT. So that's why I added this. So I made this patterned set rather than just working with a subset of Z. So this is, these are not real valued random variables, these are set valued random variables. So when I'm talking about almost sure convergence, I have to tell you the topology. So here the topology is the chromoplastic topology. So to make sense of that, I have to make this set pattern up. I cannot work with a subset of Z. So that was the point of that. This might happen. Otherwise, as I have defined, BT is just a subset of Z. So it is singular in some sense if you view it as a subset of R. Okay, so what are the conjectures? D is convex. Yeah, what I was saying, let me just get back to that. So what does mild conditions mean? Usually means that, I'm not going to say precise hypothesis, these are conjectures and not theorems. So in general, it means that it has enough moments, and sometimes also means that it has no atoms. Okay, so some of the results, these you can show for atomic measures. The conjecture I'm going to write here is not true for all atoms. And yes. Larger?
Yeah.
Okay. This size is okay? Is this size fine? Everyone can see? Okay, yeah. Thanks. Yeah, whenever you can't see anything, just stop. Okay, so what does that mean? So, this set B, as you can see from the definition, has all the symmetries of the lattice. It is symmetric with respect to permutation of coordinates, symmetric with respect to rotation of 90 degrees, Z2 and all. But it is not rotationally invariant. Because of the underlying lattice structure, you do not expect that the limit shape would be actually a Euclidean ball. It is, I don't think it is known, but it is widely believed that the limit shape has some lattice effects in it. But what is expected to be true is that if you locally look at the limit shape, the boundary of the limit shape, it still looks like a circle. It has a quadratic curvature. There's a positive uniform curvature around each direction under mild conditions on them. So that is one of the big open problems to show that under any general hypothesis this happens. Okay, I don't think there is a single model of first passage percolation that is known for which you have this sort of behavior. Although there are results along the line saying that almost every distribution has this kind of behavior, but not like a single example for which you can show that this behavior happens. Yes.
What is the reference?
So this is Eric Betts has this work where he does this convex analysis, which where he shows, so you think of this limit shape as a convex functional of the distribution, and then you use the fact that convex functions are almost everywhere differentiable. So it's
yeah. Okay.
So no. Yes.
What's equal to almost?
Well, almost everywhere in the sense that you have put a measure on the space of distributions, and so not So there isn't one example where you can show that it has positive curvature almost every. Of course, there are some basic geometric argument that will tell you there are at least 4 directions where you have positive curvature. But for example, you can have L1 ball. So if this distribution F was degenerate, then the limit shape would just be an L1 ball. So there would be exactly this 4 distributions of 4 directions of positive curvature. But the belief is that you have, if your distribution is sufficiently non-degenerate, non-atomic, and has sufficiently high moments, you will have locally your limit shape would look like a quadratic curve. Okay, so this is wide open, and then there are sort of, so this was the first order behavior. Of course, as probabilists, you are not satisfied with just understanding the mean. You want to understand fluctuations. That means you want to understand the variance. So let me just. Was there a question? Yes. Again, can you repeat?
He's asking if the limit would be almost everywhere smooth.
Okay, so the belief is that it is smooth actually under mild conditions, but it is not known. It is not known for any specific distribution of waves. So you believe that if you put enough moments and enough regularity on F, then it is actually, the boundary is actually a smooth curve, but it is not known. There are examples where it is not smooth, it has sort of flat pieces, but those examples are all sort of atomic measures. So
what do they typically look like in dimension?
Sorry?
What do they typically look like in dimension 2?
So it is somewhere between the L1 ball and the L infinity ball, but nothing more can really be said. So there is, okay, so I didn't want to get into that, but there is a result which says that if you relax that IID assumption and simply put them to the ergodic, stationary ergodic environment, then anything satisfying the lattice symmetries, convexity, and whatever these things were written there, any shape satisfying those conditions you can get them as a limit shape. If you relax that IID to stationary ergodic environment. But if you put IID, which is of course much stronger, then you are not supposed to get that. But it's one of the biggest open questions to understand what this limit shape is. Okay, so that's about the first order behavior. We'll come back to that later. But let's now talk about the second order behavior. So the variance of. Okay. So what is known about that? So it is known that it's bounded below by a constant and bounded above by a constant times n. So it cannot go more than linearly, and it cannot decay to 0. So this is the result by Kesten from 93. By the way, I did not attribute this shape theorem. So this is shape theorem was done by a lot of authors, but the final version is due to Cox to Red, if you want. But it builds on a number of previous works like Kingman, Hamasi, Richardson, and others. So this Kesten's proof, if you can see, so it's a martingale argument, but it basically is a Poincaré inequality argument. So you can see that the derivative of the passage time is non-zero. So you differentiate with respect to the variable xe. It will be non-zero if and only if the geodesic passes through the edge E. So basically, you can show that the variance is upper bounded by some constant times expected number of edges the geodesic passes, and that's how you get this upper bound of constant times n. And people dealing with functional analysis would know how do you improve on Poincaré inequality. you use something like log Sobolev or hypercontractivity, right? And that's exactly what is done. So the best known upper bound till date, it's so it was done first by Benjamin from in this 03, but it has been improved on. So they did it for binary edge weights, where edge weights can only take two values, but now it has been improved. So they used hypercontractivity, but now using log Sobolev for a much more general condition for this. But this is kind of the best thing that is known so far. Upper bound of n over log n and lower bound of constant. So in dimension 2, there is a slightly better lower bound known, which is a constant times log n. Okay. So as you can see, there is a huge gap. And here comes the next conjecture. So this is a conjecture about exponents. So there is this chi. So it says, so the standard deviation grows like n to the chi, and this is, so I write it for E1, but the general conjecture tells you that whatever direction you go, it grows in the same rate. So it's the same exponent, which tells you how the fluctuation goes in different directions. So of course, this conjecture remains wide open, and then there is a debate even among physicists whether this inequality should be strict or not. So whether or not variance actually grows polynomially. So the special case, which I now come to, is d equal to 2. There it is actually conjectured that chi is exactly 1/3. But even physicists are not unanimous in deciding whether for large enough dimension the fluctuation exponent chi should still be positive. So some people argue that there is a positive upper critical dimension, meaning that up to some dimension there is the variance grows polynomially, and beyond that dimension the variance actually grows. If it grows like subpolynomially. And then some others argue that the upper critical dimension is actually infinite. So for all dimensions, the variance grows polynomially. But it is generally believed that this exponent chi decays with dimension. But there is no precise, beyond dimension 2, there is no precise conjecture for what the value of chi should be in other dimensions. And this chi, this 1/3 exponent comes from the analysis of the so-called TPZ equation. So there is this universality class attributed to Kardar-Parisi-Zhang. So see, as I have, so what I have said so far, these exponents, they are not supposed to depend on the distribution f. So this should just be a function of the dimension. So these models are universal in that sense. So the exponent, just like central limit theorem, when you take sum of IID random variables, mean zero IID random variables, their growth is like square root n. It does not depend. The fact that they grow like square root n does not depend on which distribution you are summing, right? So that's a content of the central limit theorem. So just like that, here also the models are supposed to exhibit a universal behavior in the sense that no matter what the distribution f is, as long as it satisfies some mild regularity condition, the exponent, the fluctuation exponent would be the same. Okay. And in dimension 2 at least, these models are believed to belong to the so-called Kardar-Parisi-Zhang universality class, where the large-scale behavior is governed by the KPZ equation, which is a stochastic partial differential equation, which is imposed as it is, but Martin Harris-Field's model was on the work on how to define the theory of regularity for such for KPZ equation. So we now know how to define a solution for the KPZ equation. But anyway, so what these people did in the famous paper from 1986, they did what one would say renormalization analysis of the KPZ equation, and they obtained this exponent 1/3 from there. So that's how this exponent 1/3 comes. But in higher dimensions, there does not exist any specific conjecture like that. Okay. So one other. So far I have talked about the first order behavior and the second order behavior, and let me now come to the third question there for geodesics. So about the geodesics, so what sort of things that we want to understand? So this is 0 and that's 1. And say this is the geodesic. So what we want to understand, one of the first things that we want to understand about the geodesic is what is the so-called transversal fluctuation. So what does that mean? It means that I look at the smallest strip around the straight line joining the endpoints, such that the geodesic is completely contained in that strip. And height of that strip, which I call the transversal fluctuation of the geodesic, and I denote this by TIFR of strip length. So there is a conjecture. So this also comes from so the precise value for d equal to 2 will come from the KPZ analysis. But the conjecture is that there is a psi such that the transversal fluctuation approximately grows like 10 to the psi. So this is a different exponent. So chi is the scaling exponent for fluctuations of the passage times, and psi is the scaling exponent of fluctuation of the geodesics. And one of the conjectures is that the two exponents are related by the following relation. So this is what the relation. So in particular, in d equal to 2, we have this exponent pairs 1/3 and 2. So these are all conjectures. All conjectures, no theory. So there are actually some related models of last passage percolation rather than first passage percolation, where we are working with the maximum rather than the minimum, and we're choosing some specific distribution for edge weights, for which these exponents can actually be rigorously determined. So these are the so-called exactly solvable models of last passage percolation. But for no known FPP models, these exponents have been verified. Okay, so one final conjecture I want to state before I want to also spend maybe last 10 minutes of my talk saying something that would be of interest to progress. So let me just state one more conjecture about fluctuations. So remember, I have erased this theorem, but so remember that this quantity divided by n converges to some number mu. Okay. So I know this difference is sublinear, and then this difference I can write as difference of this minus its mean, and then plus the mean minus the long-term value. So in the FPP literature, this part is called the random fluctuations, and this part is called the non-random fluctuations. So this is just a real number. There is no randomness here. So there is an expectation. This is also a real number. So this part is called a non-random fluctuation. And the conjecture, well, okay, my conjecture part was too narrow. So the final conjecture I want to write is that this is also supposed to grow like an exponent n power gamma, and the conjecture is that gamma is equal to pi. Gamma is equal to pi. Okay. So all of these are conjectures. Different conjectures about different types of fluctuations. Okay. So now let me tell you what sort of things people have been doing.
There's also a physics heuristic behind this last conjecture.
Well, I'm not completely sure. The last conjecture actually, okay. So what I can say is that it is true for the exactly solvable models where you can actually solve it. And frankly speaking, there is no reason for it to not be true, because this is, you are splitting up the fluctuation part, fluctuation into two parts, and if one part were to dominate the other, then of course we don't know that for a proof, but one can actually prove a version of that conjecture to assume something stronger on traffic sciences. Okay, but let's say a little bit about, so why are these questions so difficult? So these questions and conjectures have been around for like 50 years, or at least KPZ is 86, so that's almost 40 years. And many people have tried to solve this thing. So why haven't there been much success? There has been some success, and I'll come to that. But the primary difficulty has been, or one of the primary difficulties is the lack of understanding of P. So it is fairly well understood how the behavior of the limit shape is intimately connected with the behavior of the ZSX and the fluctuation exponents. But we are stuck at this very basic step because we don't understand essentially anything about the limit shape. So one strand of work which was pioneered by Chuck Newman and his collaborators since the 90s was to study these models under some assumptions which we believe to be true in general. So you assume something about the limit shape, something like this, and then you try to see what can you say. Okay, so this is the line of research that Newman pioneered since the mid-90s. And parallelly, there was also another line of research which was to modify the model itself. So instead of proving conditional result, you modify the model such that you will be able to verify those conditions for the modified model. Okay, so these were sort of two parallel lines of research that has been going on over the last 30 years or so. And the results, so they are kind of parallel progress in these models. So let me say a little bit about both of these works. But before that, let me just introduce to you one model which will satisfy this condition. So I'll introduce one first passage percolation model, which will also have rotational symmetry. It will not be a lattice model, because in the lattice model I cannot have rotational symmetry. But people have introduced lots of models which have rotational symmetry. And then by rotational symmetry, you already know that the limit shape must be Euclidean bound. So you have your first conjecture for those models. So let me just tell you, so there are sort of 4 or 5 different models people have defined over the last. So this effort goes back to like 88, 89, things like that, when people first defined corona percolation. There are sort of 4 or 5 well-known models of rotationally invariant first passage percolation, where you have this where you have the limit shape as a ball. So let me just tell you one specific model. I thought I would tell you two, but I don't have enough time. So this is called a Riemannian. So how does it go? So I define say, so I start with an isotropic random field. So I start with a random field that has rotational invariance built in it, and then I try to make a Riemannian metric, a random Riemannian metric out of that. So let me just make sure that yes. Okay. Positive radially symmetric. Oh, no.
Riddhi, could you please write bigger again?
Okay. Okay. Sorry. Let me just let me just write the equation. So x, y, there I'm integrating over R2 or RD. So K is a kernel. It is smooth, bounded, positive, radially symmetric, and this B is a two-dimensional Brownian motion. So dB is just for white noise. So I'm integrating white noise against this kernel. So I get a field which is isotropic. And then to make it positive, I so this phi could be negative. I don't want that to build my Riemannian metric. So I compose it with another function which takes real line to some closed interval d1 d2 or open interval d1 d2 with the full subset. So now this psi is a positive bounded away from 0 and infinity isotropic field, and this is also monotropic. So now I can simply define my metric So I take a path, I integrate the field along that path. Okay. That gives me the length of the path. And then I can define my metric by taking infimum over all C1 or piecewise C1 paths. So this is a version of the FPP model that has a rotation. This is called the Riemannian FPP. This was introduced by Tom Lavata and Jan Way in 2010 probably. But I should emphasize that this is just the only one of many models. So there are many models for which you can define some similar rotation. Okay, so let me in the next last 5 minutes or so describe some of our recent results for models such as these, where you have symmetry, where we can now prove some of these conjectures. Okay, so let's take 3 theorems, or the versions of some of these. So theorem. So this is a very long one project. But We finished the first part like 7 days ago. So this first theorem says that for rotationally invariant models, one has so this tells you that the first passage time, if you center it by its mean and scale by the standard deviation, it has stretched exponential tails. We don't quite show exponential tail, we show stretched exponential tail. This theta is some number less than 1. It's not very important what that number is. But we have concentration at the standard deviation scale. And this, okay, if I have time, I will tell you later why this result is important, but let me tell you a couple of consequences of this theorem. So theorem 2, same authors, same paper, and same models, so I'm not going to write it again. So what we show is that the transversal fluctuation which is a version of this conjecture. So the conjecture chi equal to 2 xi minus 1, it tells you that the standard deviation, the transversal fluctuation exponent is 1 plus the standard deviation exponent divided by 2. This is exactly what we are showing. N times the standard deviation. So this is n times n to the chi, if chi was an exponent. So this is n to the 1 plus chi by 2, and that is the transversal fluctuation. So we are not showing exponents exist, but we are showing that the relationship between the two quantities is exactly what is determined by the exponents. That's theorem 2. And theorem 3 is about the non-random fluctuations. So we show. So notice that by subadditivity, we know that that quantity is always positive, because Spectator's lemma tells you that the limit is the infimum of all such numbers. So this quantity is actually always non-negative by subadditivity. So what we can show is that this quantity is, so this is basically a version of this conjecture. So we can show that the non-random fluctuation is upper and lower bounded by some constant, some positive constants times the standard deviation. Okay, so these are the results. So these are all for. So we write our theorems for rotationally invariant FPP models which satisfy a bunch of hypotheses. All known rotationally invariant FPP models, including the Riemannian FPP model that I described, actually satisfies those hypotheses. So we have these results for some specific model. Now, unlike many other results which have existed, which I'll tell you if I have some time. How much time do I have? 10 minutes. Oh, I have 10 minutes. Okay. So then I can tell you a lot more. So of course, so there have been results along these lines before. So it started with a famous paper of Chatterjee in about 10 years ago, 10, 12 years ago, where he basically proved this conjecture, this equation, under an assumption which looks slightly different, but is essentially similar to our theorem 1. Okay, so he assumed that there is a exponential concentration at the standard deviation scale, which is the same in all directions. And then using that, he proved this conjecture, this KPZ relation. So he assumed a little bit more in the sense that exponents exist. And then he got this scaling relation chi equal to xi minus 1. And then there have been subsequent improvements. There is a work by Affinger and Damron which in some sense simplified the hypothesis that Shodrov had. And much later, Ken Alexander, a couple of years ago, he simplified the assumptions a bit further. But from what I understand, I don't know if Shodrov will agree with me, these works were not fundamentally changing the assumptions that he had. So the exponential concentration estimate, concentration was always the assumption. So that now for the rotational invariant model is no longer an assumption, it's a theorem. So we have a theorem which tells us that the passage times are concentrated, stretched exponentially at the standard deviation scale. And this type of estimate is extremely useful, turned out to be extremely useful for the exactly solvable models. And of late, there are also works assuming this sort of estimates in FPP model proving a lot of things. So for example, Ken Alexander has a work where he assumes essentially this and curvature of the limit shape to show that bijodicics do not exist in first passive percolation. And he also has a similar work showing the upper bound in the theorem 3, assuming something like theorem 1. So the concentration estimate is, we believe that it is extremely useful. And this kind of, for those of you who know a little bit of what I do, I have spent most of my time over the last 10 years trying to see what sort of things you can say in exactly solvable models where you have these exponential concentration of the passage times just by using that. So exactly solvable models have a lot of structure, a lot of algebraic identities, but there are a lot of things in the last few years where you try to understand how much you can say with just assuming the concentration and say the curvature of the limit shape, which is also known in the exactly solvable model. And it turns out that you can actually say a lot. And hope will let us transfer many of those results to some of the FPP models. So that's one of the reasons we think that this exponential concentration estimate is going to be very very useful, or we hope that it is going to be very useful. There are also some other things that we can say using this. This is, as I said, this has been going on for many years. This project has been going on for, and this is only the first part that I'm reporting on. But in a later half, using this estimate, in particular using using theorems 1 and 2, what we will show again for rotationally invariant model, but not all of them, we will require another extra condition, which is the FKG inequality, which will be satisfied for the Riemannian F model and some other models, but not all the known rotationally invariant FP model. For example, if you are familiar with the Voronoi F model, again, so this part of my talk is meant for the people who are familiar with the literature. So, if you don't understand, ask me later. I'll explain. But there are these other models like Voronoi first passage percolation model, which is also a rotationally invariant model, but that does not satisfy the FKG inequality. So our results, these results hold for those models, but for some other estimates, we would need the FKG inequality. So in the second half of this project, what we will do is that we will show for rotationally invariant models which also have the FKG property. Using these theorems, we will show that the variance actually, the strict inequality here. So we'll show that the variance grows sublinearly in terms of a polynomial, not like n over log n is n to the 1 minus epsilon. But anyway, that's still a few months away, so I don't want to talk too much about it. But yeah, so I say something else. Yeah, so I hope the hope for this talk was to convince, as you can see, the results part is the longest part of the board, but most of these conjectures are still very, very much conjectures. So there are very interesting, precise predictions, but we are still very far away from actually being able to solve those problems. And there are many interesting open problems here. So I hope to tell you about this interesting model and to get you interested in this. So yes, I think I'll stop here. And, thanks for listening.
Are there questions?
So first thing is that I think so you assume when you say like under some additional assumptions, right, on the mod that you need that underlies the theorems, like you need to assume something about the kernel or some decay or anything. Like when you let's say when you define the Riemannian FTP,
yes.
So the kernel with respect to which you convolute the thing.
Well, we are assuming it has bounded support anyway, so that
okay.
So that is, I think, that was written. So I mean, if it does not have bounded support, then the model will have long range correlation. We don't want that.
Okay.
So we want to emulate IID FTP as closely as possible.
In the general case, you will have some finite range dependence. Right?
So this will just be, our kernel would have support just the unit ball set.
Okay.
So the correlations will, if you take 2 points which have distance more than 2 away, then the correlations will be
okay.
They will be independent.
So the next thing is that so using this, can you also kind of derive like let's say some kind of so let's say I'm just looking at the transversal fluctuation.
Yes.
And I want to look at its moderate deviation probability.
Yes.
And whether their existence similar like for Basu.
Right.
So can you also show that, and can you also show some kind of scaling relations between, like, say, if this is theta here?
So this is something that has. So Shishendu has a paper with Milind. Both of them will probably be here later in the week, where they do exactly that. They are still working on the last passage population framework, but they do not assume exact solubility. They are only assuming stressed exponential concentration for the passage time, and then they show assuming a certain exponent in the stressed exponential concentration of the passage time and an exponent at the scale at which you are concentrated, how the exponents for the moderate deviations of the last passage time and those kind of things, how they are related. So these are
this is still for directed.
Yes, but it's not. I mean, the directed thing is not very important. It's convenient, but it's not.
Yeah, so that's my question. They are not assuming. Okay, so then I see. Mm-hmm.
So what they are not assuming is that they are not assuming exact solubility. They are not assuming that you have concentration at the scale n to the 1/3. They are assuming that you have concentration at the scale of variance, and if the variance grows like some exponent, then similarly you have some scaling relations for the moderate deviations. So the point is that once you have a result like theorem 1, there are many things that you can do. There are many sort of population estimates that you can do that gives you a handle on the estimates of the kind that you are asking
okay,
for.
So then in particular, so let's say for this type of models,
yes.
So their technique kind of also extends. If they take this as input or
no, this will be technical work.
But okay,
because it's not a lattice model, you can't take bounds. You have but morally there is no sort of barrier. You have to deal with the backtrack, and there are usual things that you have to deal with, but there is no moral issues.
Okay, thanks. Last thing is a much more basic question. So when you talked about the flux, so like if I take the ball BT okay,
Yes.
and took its fluctuation, let's say, of distance, let's say, around t times the limit check.
Yes.
Is it like t to the power chi times the log factor?
That's what it's expected to be, but we don't even know the
No,
existence
like
of
assuming
chi.
that if something and then
So the main issue is that okay, so one of the major difficulties in trying to do these things without the rotational invariance is that you don't know that the chi is the same in all directions. That's a big headache. So in our models, in our results, it is not just enough to assume that the limit shape is a ball. We actually also need to know this, in some sense, all the other works like Chatterjee's works and Alexander and other following works, they needed to assume that the fluctuation exponent or the growth of the fluctuation is same in all directions.
This is kind of important for, like, say, finding regularity estimates.
Yes, this is extremely important for finding estimates when when you're varying a little bit. So because your paths are not going to follow, your geodesics are not going to be exactly straight line. Right? Sometimes they will go in some other directions, and you have to control what sort of deviation you have in those directions. So that is very important. So you do need some kind of a handle on how the fluctuation exponent changes when you vary the direction locally. So that is something we don't know how to prove.
And a very final thing, but which you don't have to answer now. Like, it's probably not possible to say any heuristic about the strict gap that you can derive from this.
Oh, that is actually very easy to. The heuristic is very easy. The heuristic comes from Chatterjee's super concentration, and you know that, right?
I have technology a lot of times.
So
thanks a lot.
Anybody else?
Regarding the variance estimate, I was wondering if there is any analog of the OSSS inequality in these settings, like using decision trees.
Yeah, Shubhajit is probably more of an expert on this than I am. So
yeah, probably nobody has tried. No. Another way to improve the point.
I mean, there are these are all influence inequalities, right? So I don't know, but I don't know if you know. Right. I have not seen it.
Okay. Are there any questions on the chat?
No, there is only one participant.
Okay. So let's end the speaker again.